So you've probably never seen one of these things in real life, but I bet you've seen one of these. You've probably seen those many, many times. Those are all over the place here in Oklahoma. These little bugs that can skim across the water. How do they do that? How can those bugs stay on the water and swim on top of a liquid? It's almost like they're standing on the ground, but they're standing on a liquid. The way that they do this is actually using surface tension. There is an amount of force that is required to break apart the molecules at the top of the water, and the bugs just don't apply enough force to do that. And this is all due to intermolecular forces. So at the very top of the water there, at the edge of the water molecules that are all attracted to each other, again, this is the intermolecular forces we've been talking about up to this point. Those water molecules are attracted to each other, but at the surface, they're not being pulled in every direction equally because there's no water, at the surface. There's water in certain directions, but not in every direction. Whereas water molecules way down in the middle, the water molecules being pulled equally in every direction because there's water in every direction. But up here at the surface, the water molecules are only either pulled in the plane of the surface or pulled downwards. And what that ends up doing is it ends up actually concentrating the water at the surface. It ends up like kind of compressing, in a sense, the water there at the surface of the liquid. And again, those water molecules like each other. They are participating in hydrogen bonds with one another. They like being right up close and cozy with one another. And so if something wants to come along and push them away to break those intermolecular forces, it's going to take a little bit of force to do that. Now for us, that's super easy because we're ginormous. We're huge things. It does not take much force for us to break those water molecules apart. But those little water bugs, they have these tiny little legs that spread out their weight over a relatively large area, and they actually don't apply enough force on the water to break the hydrogen bonds. And so they actually can stand and move around on the water on this surface tension. That is a result of those intermolecular forces. This is also why water tends to bead up. If it's on a surface that is very, what we call hydrophobic, so a very, very non-polar surface, the water really likes itself. It has no interest in interacting with the hydrophobic surface, and so it will move to try and maximize its interaction with itself. It's very self-absorbed this way. So it will maximize its the amount it touches all the other water molecules and minimize the amount of interaction it has with the hydrophobic surface, which is why you get these little spheres where there's as little surface contact with the hydrophobic surface as possible. And you can get really super hydrophobic surfaces where it is practically a perfect sphere sitting on top of the surface, which is pretty amazing. So again, the higher the intermolecular forces, the greater the surface tension. Same type of thing with viscosity. Viscosity will increase with greater intermolecular forces. And this has something to do with intermolecular forces just in terms of the types that we were looking at before, dispersion and ion dipole and things like that. But it also has a lot to do with the shape of the molecule itself. If you have a big chain, like you see down here, big chain type molecules, those actually can physically get caught on one another. And the greater the intermolecular forces there, the more easily they get caught as well. But the higher viscosity oils, for example, those tend to have very long chains of hydrocarbons that easily get wrapped up in one another, and so they literally just move more slowly. The liquid moves more slowly because the actual molecules themselves can't move very quickly because they're wrapped up in each other and they're getting caught on one another. And so the lower the intermolecular forces, the higher or the lower the viscosity, the more easily they move, essentially. So here you can see here the lower viscosity number oil moves a lot faster, it pours a lot easier, and temperature will have an effect on this as well, which if you've ever changed the oil in your car, you know this. You know this to be true. If you've ever changed the oil in your car while it was still warm. I hope and pray that you never changed the oil in your car while it was still really hot, because that could really hurt you. But if you were kind of impatient, you're like, I'm sure it's cool enough by now, and you open up the oil pan at the bottom of your vehicle and it's still warm, you can tell it flows a lot faster when it's warm than when it's cold. If you have cold oil, it'll still pour, but it's very deliberate, very slow pouring. Whereas if it's warm, it shoots out of there like water, essentially. So the higher the temperature, the lower the viscosity, the faster it moves, essentially. Capillary action is the same way. This is another physical property, or chemical property that we see that is dependent on intermolecular forces. So this is when you have liquids that will actually travel against gravity up a small tube. So you can see here water is traveling up this glass tube. The reason that it's doing that is because water is highly attracted to glass. Water and glass are both very hydrophilic, which means that they're both very polar, essentially. Hydrophilic, from the Greek, means it loves water. And because the water has those very positive, very strong intermolecular forces with the glass, the water will try to maximize those interactions, and it does that by traveling up the glass. Now, it can only do that to a certain extent because gravity is trying to pull it back down. But it will travel up a certain distance just depending on how strong the intermolecular forces are and the radius of the glass tube as well. Generally, the smaller the radius, the higher up the tube the water will go, because there's a higher percentage of the water that is interacting with the glass in those very, very small tubes. This is actually how, or one of the ways anyway, it's not the only reason or the only method that is used, but trees are able to pull water up from their roots up higher up into the trees, into the leaves and branches and things through capillary action as well. Water will move up tiny little, like the tree version of a blood vessel, essentially. Again, not a botanist, but the water will move through tiny little vessels there and move up against gravity just because it is very, very attracted to the thing that is making up that vessel that it travels through. And you've also seen this if you've ever given blood before. They will test your blood for its iron content, and they usually prick your finger, and then they will take this little glass, I don't know exactly what to call it. I think this is kind of an older version of it. The newer ones are more like a plate. But they'll take it and they'll kind of just barely touch the edge of it to the blood, and the blood will just kind of just get sucked right in to the little plate. And that's because of intermolecular forces there. It's capillary action. The blood is very attracted to the stuff that's inside of it, and so even though there's gravitationally speaking, it shouldn't want to move. It should just want to stay where it is. It wants to go to maximize those intermolecular forces. All right. I think we'll make us a nice short video here for this one. So we'll leave it there, and the next one we'll talk about phase changes and start talking about what is actually happening in terms of intermolecular forces with vaporization, condensation, and what we can do to affect the rates of vaporization and condensation. So see you in the next one.